So, welcome to Chapter 12. You have made it to the very last chapter in the course, and I know that you're excited about that, but everything we have done this semester has been building to this point. So, this is not the chapter that you want to say, oh, it's the last one, I'm going to slack off, I'm going to, not give it my full attention, because this is the pinnacle of statistics when we get to talk about regression analysis, and this is everything that we've been building up to. So, this is the biggest chapter that we've covered. This is the biggest and most important concepts that we've covered. So you want to make sure and hang in there for one more chapter and really try to grasp this information, because this is everything we've been working towards. So we're going to start by looking at the introductory case. We're going to be using this data throughout the chapter to look at regression analysis and analyze the data. So we're told that a 2010 study showed that consumers in 26 different cities made debt payments, which I'm assuming are payments on credit cards, car payments, student loans, things like that, ranging from $763 to $1,285 per month. So we have this economist who believes that income differences are the main reason for the disparity. She's unsure if unemployment actually impacts the disparity or not. So we're going to look at some regression analysis to examine this a little bit more. Now, first of all, we're going to use regression analysis to make predictions for debt payments given values of income, and then eventually the unemployment rate. And then we'll go back and look at those goodness of fit measures that we looked at a little bit in the last chapter. We're going to look at them in some more detail here, and then look at significance in the unemployment rate at the 5% significance level. So just starting here in this first video, let's talk a little bit about what simple linear regression is. So regression analysis is allowing us to analyze to see if there is a linear relationship between two variables. And if there is a linear relationship, is it a positive relationship or a negative relationship? Now, the two variables that we're going to be looking at are called, your book calls it the response variable, but you'll more often hear it called the dependent variable. So that is our Y variable, as we'll commonly come to call it. And then what your book calls the explanatory variables, or the independent variables. And those are more commonly referred to as the X variables. So again, if you're taking notes, which I certainly hope you are, I want you to write down in the margin of your note, the X variable is the explanatory variable, which is commonly called the independent variable. And then the Y variable is the response variable, or the dependent variable. So we're really looking to see if the X variables have a positive relationship, have a linear relationship with the Y variables. And is that linear relationship positive or negative? So again, we're going to use those explanatory or independent variables to predict and or describe the response variables, or describe changes in the response variables. Now, we're going to eventually look at the correlation coefficient, and this may establish a linear relationship. It may even tell us if it's a positive or negative linear relationship, but it can't tell us if one variable causes the other. So I know the words dependent and independent kind of imply that the independent variables are causing these changes in the dependent variable, but linear regression can't tell us if there's a causation. They can just tell us if there is a correlation between the two. So again, that's something you want to be very, very careful with in your interpretations. So when we're looking at these, we're looking at what we call deterministic versus stochastic relationships. So if the value of the response variable, or the dependent variable, is uniquely, meaning almost completely 100% determined by that explanatory or independent variable, then we say that the relationship is deterministic, and that the independent variable determines the dependent variable, or the explanatory variable determines the response variable. But oftentimes there may be a correlation between the two. Maybe it has some impact, but there are other things that impact this relationship as well. And so, as in many of the cases, we say that the relationship is stochastic, because while it has an impact on it, it's not the only thing that affects it. So in regression analysis, we're going to include an error term. You'll see it in a couple of slides when we look at the formula. It's like kind of a funny E shape. It's the Greek letter epsilon. And that's what we use as our error term that kind of accounts for all of the other things that we haven't accounted for in our regression analysis. So the most simple linear regression formula is y equals, now that funny B, remember, is beta, the Greek letter beta. So beta 0 or beta null plus beta 1 times x plus epsilon, where y, again, is our response variable or our dependent variable. Y is what we're searching for, and x is our explanatory or independent variable. And then you see that e, or the epsilon, is the random error term. Now, if you just look at the first part of this equation, kind of ignore the e, the plus e at the end, where you have y equals beta null plus beta 1x. If we were to substitute in there some different variables, in fact, instead of beta null, what if we called that b? And instead of beta 1, what if we called that m? Now you would have that y equals mx plus b formula that we're all familiar with. It's just the equation of a line, or y equals ax plus b, however you learned it. So we can substitute those same parameters on here and say that beta 1 is really the slope of our line. Really what we're searching for is a line where beta 1 is the slope and beta null is the y-intercept. So again, you're all very familiar with the equation of a line by now. We use that for a lot of things. We even use it in accounting, which is always shocking to students, but we're looking for that linear relation. So really what we're solving for is what is the y-intercept and what is the slope of this line. And then once we know that, we can plug in various values of x to determine what y would be, or we can estimate y would be. So using sample data, because that's how we get our slope and intercept, we use a sample. So we're going to say the little b1, again, is the slope from our sample data, where the little b null is the slope, the y-intercept of our sample data, and then y hat is our prediction. Now, the error value, that epsilon, the residual, is going to be the difference between what the value actually is in our sample and the predicted value, the y hat. So we're going to see that difference when we look at the graph here in just a moment. So in this case, we've graphed a scatter plot. We have debt payments and income. So we have our X and our Y. Our debt payments are the X, and the Y is, the income is the X, and the debt payments are the Y. Now notice how we've graphed it. We've graphed the X, the independent variable, on the horizontal axis, and we've graphed the y, the dependent variable, on the vertical axis. So we're familiar with this from graphing. So we've graphed the scatter plot, all of this data that we collected in our sample, and then we used regression analysis to fit a line, to fit a trend line between the data. And we're going to do this in Excel in just a minute. Now, how Excel or any statistical package uses this data to fit the trend line is they calculate the difference between the line and the actual observed value. So we have our difference between y and y hat, or that e or epsilon, that measure of error, that residual value. Now, when we call it least squares regression, they're going to square the difference and fit the line so that the difference between each one of those points and the line is at its minimum. That's the reason we call it least squares regression. Now, thankfully, we don't have to do this by hand. We're going to do it in Excel because, let me tell you, as someone who is old enough to have done this by hand, they did have computers when I was in college, but we did still have to do this by hand. It's a booger, okay? It's just not fun at all. But once we've determined the slope and the y-intercept of this line, now we can use it in a formula to predict what y would be, what our response variable would be at various levels of independent variables. So in this case, we could predict what debt payments would be at various levels of income. So again, least squares regression, or ordinary least squares regression, as it's sometimes called, OLS, is doing exactly that. So that error sum of squares, which you've seen before, you saw that in the ANOVA table back in chapter 11, that is the sum of all of those differences between the observed value and the trend line squared. So these are just the formulas that we would use to calculate, again, our slope and our y-intercept in our equation. Again, obviously, these are kind of nasty looking formulas, and especially when you think about you have to do this for every single data point. So the larger the sample, the more you have to do it. But thankfully, we have Excel that's going to make it very easy for us. So we're getting ready to jump into our Excel. So you want to open your chapter 12 Excel workbook, and we're going to go to the debt payments page. So again, here I am in our chapter 12 workbook. I'm on the debt payments page, and you'll see that we've got our 26 metropolitan or cities down here on the left, and then we have the debt payments listed in column B, the income listed in column C. Now this is income in the thousands, so when you see there that it's 103.5, that's $103,500 is the average level of income. And then we see unemployment. So we're not going to deal with unemployment right now in this video, but we are certainly going to come back to it in a future video in just a few moments. Now, before we construct our scatter plot, that's what I want to do first. Now, technically, we don't have to construct a scatter plot in order to perform regression analysis, but it's helpful because it gives us a visual, a good visual of what the data is doing. It makes it very obvious for us to determine if it's a positive or negative relationship, or if even there's no relationship at all. So the first thing I want to do is go ahead and construct that scatter plot. Now, here's the thing. When we construct a formula in Excel, when you grab, or not a formula, a chart, when we grab the data, Excel automatically by default chooses the first column as the X and the second column as the Y. So remember, our X is our independent variable and our Y is our dependent or response variable. So in our data, income is really our independent variable. We're looking to see if income has an effect on debt payments. So the first thing I want to do is rearrange my data so that I have my X variable on the left and my Y variable on the right. In fact, I'm going to go ahead and change this income. I'm going to remind myself that that's my X variable and that my debt payments here are my Y variable. So I'm going to highlight the whole column B. I'm going to click Insert. That inserts a column to the left. Now I'm going to highlight all of column D, cut, and Control V to paste that in there. So now I have my X data on the left and my Y data on the right. So to construct a scatter plot, we've done charts in Excel before. I'm just going to grab all the data, including the header. I'm going to click Insert, and over here under Charts, this one that looks like a lot of dots is the scatter plot chart, and I'm just going to choose this one here to the left. So it automatically puts the title in for me. I can change that to say, you know, whatever it is that I want it to say. How do I want to change this? Let's say, maybe we'll just call it debt payments. All right. Now, First thing that I want to do, I can clearly see that this data is trending upwards. In fact, it's pretty obvious that this is a positive related variable. So in other words, that income has a positive relationship on Y, that as income increases, debt payments also increase. If the data was trending downwards, then I would say that it had a negative relationship. And if it was just a straight line across or no discernible line, then we would say that, maybe there was no relationship at all. Now I can go ahead and insert a trend line. So if you'll just click in here, click on the actual dots, and then right click, we can just say add trend line. And we want a linear trend line. So you notice that it's added in there. Now one thing that I want to do is I want to change these axes because they're really big, and all of our data, if you'll notice, ranges from just around 60,000 to a little above 100,000. That's our income levels there. And so I have a lot of blank space on my graph. So I'm going to go over here. If I click on this y-axis, it pops up axis options over here. And I'm going to click on this one that looks like a graph and click on axis options. And I can change the minimum to, I don't know, let's make the minimum 600. And we'll leave the maximum of 1400. Now, notice that now my graph has shifted a little bit, so my minimum is not at 0, my minimum is at 600. I can change the units. If I didn't want it to go every 100, I can make it go every 50 or every 200. I also want to change my x-axis, so again I'm going to click down here on my x-axis. I want my minimum to be, I don't know, let's say 55. Press enter. So now I have a graph that looks more like what I'm expecting, where it's really kind of zoomed in on the data. Again, I can also add titles, go up here to add chart elements. I can add axis titles, horizontal. I can change this to be income levels in thousands. I can add chart element here, vertical. I can change this to be debt payments. So now I can use this trend line to predict, for example, if someone has an income of $95,000, I can follow this up and I would expect their debt payments to be about $1,200 a month. So I'm visually analyzing that just based off of the graph that I see. Now, let's move this graph out of the way. I didn't mean to quite do that. Let me grab the whole graph. Let's just drag this graph down here to the bottom. Let's move that out of the way. And let's go in and actually do our regression analysis. Now, I'm going to go to my data tab here, click over, and to data analysis. And now again, I see I have regression as just one of my options here. We've been in this data analysis tab a lot lately, so I'm going to click regression. Now, one thing I want to point out to you, notice how the input range seems to be a little bit opposite. It asks you to input the Y range first and the X range second. So one of the biggest mistakes that I see students make is they just put the wrong range in the wrong spot. Especially if you've just reordered your data so that it's X then Y because you've graphed it. Well, now it's going to come up and ask you for Y first. So just be careful that you're putting it in the right spot. So I'm going to click my Y range and I'm going to select C1 all the way down through C27. And my X range is then going to be B1 through B27. All right, I do have labels. I'm going to click that. My confidence interval is already set at 95%. I don't want my output range to be a new worksheet. I'm going to put it maybe right up here in D1. Let's just say that. And then I'm going to click OK. We're going to not mess with the rest of that right now. Yeah, it's okay if it overwrites existing data. I'm not going to save this, so make sure that if you put yours there that you maybe move it over to the side so you don't get rid of that unemployment data because we are going to need that later. So here I see lots of data. It gives me lots of data, and we'll come back and look at a lot of these in some of the later videos. But the main things that I want to focus on right now are down here under the coefficients where it says intercept and income. I'm going to highlight these for us. So this tells me that my y-intercept, where x is equal to 0, my y-intercept is 210.2976, blah, 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 blah. Now, it doesn't always make sense to interpret the y-intercept as if x is equal to 0. In regression, in our studies, it doesn't always necessarily make sense. And we'll see some examples of that later on. But in this case, we could say, for example, if income was 0, then the debt payments are on average $210.30. Which kind of makes sense in this example because even if you have 0 income, you might still have debt payments to make. But what this does tell me is that income, x, so this is my slope, if you're going to look at it that way, this is my slope, is 10.44. So a way that we can interpret that is as income increases by $1,000, we predict that debt payments will increase by $10.44. Now, the reason I said $1,000 is because income, remember, is reported in 1,000. So think of our slope as rise over run. As income increases by 1, which in our case is 1,000, then the rise, the increase in our slope is going to be $10.44. So every time we get a $1,000 pay raise, we make an extra $10.44 in debt payments. So we could even go so far, again, I'm going to move this graph down a little bit here because I want to be able to see data. We could even go so far as to write this out as an equation where we could say that debt payments equal 210 point, let's just round to 30, plus $10.44 of x. Okay, in other words, x, remember, is our income level. So now we can sub into that formula any level of income and determine roughly what the debt payments would be. So earlier we said if our income was 95, in other words, $95,000, we would make approximately $1,200 in debt payments. Well, let's test that theory out. So let me write my equation. So equals 210.30 plus 10.44. Now I'm going to plug in, instead of x, I'm going to plug in 95. And guess what? According to this predictive model, our debt payments would be $1,202.10. So again, very roughly close to what we saw on the graph. So again, we can use this to make predictions about what our debt payments would be given our sample data.